Thank you all for coming, and of course, thank you to the organizers for organizing this workshop and giving me a chance to speak here. I'm going to be talking today about some joint work I did over the summer with a PhD student, Daniel Teixeira, at Dalhousie University. And this was kind of an interesting project because I think one of the punchlines that I wanted to get to today is how like, sort of the question of how to think about symmetries. Symmetries in fermionic theories, QFTs. But I think that before you talk about a symmetry, you have to think about like, what is the structure of a QFT that you're allowed to, what type of equivalence condition you want to specify on your QFT. Indeed, without the right equivalence condition, then it doesn't really even make sense to talk about a symmetry. And so when you want to think about fermionic QFTs, you can also think about fermionic QFTs in the presence of a TQFT that has emergent fermions. So usually you would want to define a QFT kind of defined up to up to some invertible QFTs, and this is a pretty good notion of what you might want to, like a condition you will want to put on your QFT, right? And then using this condition, then you can study, okay, what are the automorphisms or something like this of my QFT that preserves it maybe up to some invertible thing. So today I want to show you an interesting thing that you can do. I want to present an interesting construction. So I'll present, so the goal is to give a construction where I modify the symmetry of a, so every time I say QFT, I really mean a fermionic thing, a QFT, but the QFT itself is invariant. And so this might be, this statement here might be a little bit startling, right? How could I say, well, I have a quantum field theory, I studied it, I know all of its symmetries, you did something else, but you're saying the theory is the same, but now has a different symmetry. And this is the conundrum I want to discuss today. And I think that one of the ways to answer this question comes from something that was inspired by this discussion, category theory, which is the study of like valence and univalent categories. So as I said, the structure of symmetries inside quantum field theories, you need to impose some sort of equivalence condition here. And sort of this equivalence condition is going to be the thing that I'm going to tell you about. And it's going to be the way I'm going to modify the QFT to have a different symmetry while keeping it the same. So it's really what I mean by this invariant thing here. So in a broader sense, why do I think this question is important? I think in a broader sense, this question is important because, when you study quantum field theories in general, it's really hard to just study a quantum field theory by itself. You really want to study families of quantum field theories, and you want to understand in particular the space of quantum field theories. And the space of quantum field theories, may arrange themselves into some sort of category of quantum field theories, and I want to know what is the properties of this category of quantum field theories. Well, usually speaking, the category of all categories should be something that's univalent. When you study the category of all categories, which is 2 category, cat is a univalent. So the analogy I want you to draw is that this is the category of all, let's say, 1 categories. the category of all QFTs is something where an object inside is a QFT, but it's a univalent category in the sense that all notions of isomorphisms, isos are equivalences. So that's sort of the univalent point of view. And then there's also a thing that I've kind of rebranded along with some other people as this concept of a valent category. And then in that sense, you don't always have to you can say that there are such categories where not all isomorphisms are kind of the same type of equivalence. But this is maybe not what you would want to do in like an actual quantum field theory sense. Maybe you would want to say the category of all quantum field theories should actually be a univalent thing rather than a valent thing. I don't actually know the answer to this question. I actually think that it should be a valent thing. Sorry, I actually think it should be a univalent thing, but we'll see that if you really want all notions of isomorphisms to be equivalences, you need to say a little bit more about kind of what you want to probe. I realize this was a little bit vague, but hopefully that was somewhat motivating to why I'm even studying this question. So here's the construction I'm going to give. Yeah. So of course, I can have two different ways of things being isomorphic in the category. And I'm saying that maybe I'm isomorphic via morphism, maybe I'm isomorphism via some kind of path equivalence. But then no matter how I got between the first thing and the second thing, I'm just saying that I just identify the first and the second thing. But and this is a pretty good notion. Probably you would like to say that in quantum field theory, there's one type of quantum field theory and another type of quantum field theory. I can get between one and the other. But I should still identify them as being equivalent, right? It didn't matter how I did it, but they're the same. So that's the univalent setting. And now I'm saying that there are certain settings in category theory where you don't have to pick this univalent setting. You could pick a valent setting where you distinguish between these two types of isomorphisms. And now the question is, in physics, what type of thing do we actually want? So this is the question I want you to bear in mind as I'm going through this discussion.
There's a deformation that takes you, let's say, some path in space.
Right.
QFT that takes you from CFT to the gap.
Right. So imagine I have so indeed this is the type of question you would say. Suppose I have two types of deformations that go between two types of things. You would say that, well, of course these two are the same thing. Didn't matter if I took path 1 or took path 2 to identify the two things. They should be I should say these two things are somehow like related to each other.
So when you say that two field theories are equivalent, are you saying all the observables in the two theories will be the same?
So that's maybe too stringent of a way of classifying things. There is a way of saying equivalences in the topological world where I have some gapped boundary between one thing and another, and then I would say that is a notion of equivalence. That's kind of a Morita equivalence. To say a quantum field theory and another quantum field theory is the same on the nose is way too much information. That's almost never the type of equivalence I wanna pick. So to say, given two quantum field theories, how do I know they're the same? Well, one thing you could do is take all the observables, take out kind of all the correlation functions here and all the correlation functions there, see if they all match. But that's kind of a really tall order. So that's kind of not the type of equivalence I would like to make.
Short answer to that question. Deformation class. That's kind of deformation class. The answer you are defining equivalent in that sense of deformation class.
Yes.
Such with a symmetry and anomaly match that can deform.
Yes. Yes. That is a notion of equivalence. Well, univalent is saying so that's one type of equivalence, and then you can have another type of thing. And I'm saying whatever one you choose, these two things are the same type of. These two things are the same. So one thing you gave was an isomorphism, and another was an isomorphism. And I'm saying these two isomorphisms are the same. I think let me go right to the construction, so you can see sort of what's going to happen and why I think this question is important. So I'm always going to be in 2+1 dimensions. So I have a theory T, 2+1d, and so everything is always fermionic. And when I say fermionic, I really mean that this thing couples onto some spin structure. And another way of saying this, if you like to kind of understand the local aspects of your theory, is that there's some local fermions, right? There's some local fermions. Which is to say that you could have like some genuine fermionic operators. You don't like you have some genuine fermionic operators in this theory. And then to this theory, I have an action by a category C, which so if I'm in 2+1 dimensions, the category of, let's say, finite, not even going to say unitary, but let's just say finite symmetries, I'll say that C is is a fermionic fusion 2 category. I'll tell you a little bit about what this means, but it's a fermionic fusion 2 category of a specific type. And the specific type that I care about is something which I'll call a strongly fusion 2 category. So in a 2 category, what do I have in general? I have kind of objects are kind of surfaces, and then I have morphisms are lines, and then you have 2 morphisms. Are points. So the specific type of 2 category I'm gonna consider definition a fermionic strongly fusion 2 category C is, well, has if you look at the loops of C, which is, so what is the loops of C? The loops of C extracts all the line operators. So you can think of this as the line operators. More specifically, this is endo of the identity inside C, and I want to say that this is equal to the category of supervector spaces. So this is just a definition for you. I don't need to define for you fermionic fusion 2 categories in general. We'll just be working with fermionic strongly fusion 2 categories. So this is the type of thing. Again, the way you should think about this is that the line operators inside here are very trivial. All I have is like kind of the fermion line, and then it's a property. That if this is true, then pi0 of C. So pi0 of C are the components of C. So in a fusion 2 category, what I have is I have kind of components, and then inside each of the components, there's an object, and all the other objects are related by morphisms. But since I have no morphisms, I just kind of have these little components that I'll call as the objects of my category. And the components is going to be some central extension of a group that I'll call GP.
So just
Right. Yeah, exactly. And it's just a fact that if this is true, then if you look at these objects, they have a group-like fusion rule. So the group-like fusion rule is given by some central extension of this. The central extension you can call kind of GF or something like this. It's going to be a central extension of a group this by some C2. Yeah, this is the fusion of surfaces. So the pi0 of this thing, or maybe I should say these are the surfaces. so exactly. So this is the type of thing that I want to act on. So like the simplest type of example you can think of is well, if GB, so here's an example. If GB is odd, so if GB is odd, then I have no central extensions, so they just split. And in that case, C, you can write it as 2vec GB, and then it's literally just tensored on with 2s. So this is kind of the simplest types of example. And so GB is odd, which means it's an odd order group, and then there's no extension with an even thing. But in general, what can I do? Well, in general, this central extension GF is something that looks like Z2. So in general, I can have Z2 going to GF, going to GB, and sometimes people call this kind of the fermionic symmetry or the fermionic group. I'll call it the fermionic group because the fermionic symmetry means kind of a categorical thing. And these fermionic groups are parameterized, of course, by some GB and some class kappa, where kappa, I'll say, is H2 BG with, so it's something parameterizing this extension. Showing up on the object layer? Yeah, so this is the theorem that Theo and I proved, that if this is the condition, that ensures that this one's actually all invertible. Yeah. A fermionic group is exactly this definition. It's an extension of a bosonic group, which is just an ordinary group that you would have, but it's extended by Z2 centrally.
So it's defined by that exact sequence.
Yeah, that's right. And the data is a bosonic group was just a group, and then a class in H2.
So GF is the bosonic group, but with some extra signs floating around.
Yeah, it's exactly sure. Yes, exactly. You can think of this as an extension of your bosonic thing by the symmetry, which is -1 to the f, if you like.
How do I see this type of things maybe from category language you set up here? Helpful to people who think quantum mechanically.
So you want to see? I mean, you're asking how does the category see the fact that you have a graded Hilbert space?
Maybe there's some intuition behind make the category language very natural to physicists and try to help maybe
what to say? So in the world of TQFTs, you can make this pretty precise because you can actually say that you could define a fermionic TQFT using this category, and then there, for example, you take like the fermionic lines, and then you can define a Hilbert space, which is the Hilbert space of like a Chern-Simons theory, but you take a fermion and then you wrap that around, so that gives you a fermionic Hilbert space. In that sense, it is quite precise because the Hilbert space of Chern-Simons is defined sort of, you can take the torus, and then you can take the line operators there, and if you have a fermionic sector, then that thing, if you act by -1 to the f, it'll say, that's a fermionic sector or something like this, if you want to define it on the torus.
So, I mean, if you're being super naive, if you have a theory of just bosonic fields, are you saying that you can quantize the theory in such a way that you bring in fermions?
I don't just have bosonic fields. I also have like fermionic fields as well. Oh, these are not the emergent fermions yet. The emergent fermions are coming in after I put in the TQFT, but this one really just has local fermions. So I'm just setting up the symmetry of the of the starting point. I haven't gotten to emergent fermions yet. The point is that this is supposed to be the symmetry you think about, because this is the symmetry that kind of acts on this theory. And then I'm going to do something to this to like change this. But the emergent fermions haven't quite entered into the story yet. Well, Juven, I don't know. I don't really think about the symmetry acting on the Hilbert space. I think of the symmetry acting on like the operators, right? And so you define some, you probably define some Hilbert space based off of your fermionic operators, right? And then you can say this is a thing which is like acting -1 to the f on some sort of, on let's say the local operators which have some amount of fermion numbers, right? So maybe you could define it that way.
Does it make sense to change the Z2, which is like fermion in Z2 to Zn?
Sure, you could do that. There are like these like parafermion type things that you could try to define. So for me, like having the Z2 is quite important because there's this whole story of how this has to do with spin structures and things like this, which I'm about to explain, like right now. So in order to get it to work with like spin structures and things like that, I really want Z2. So I have like Stiefel-Winnie classes and things like this. What it means to bosonize? Sure, yeah. As Juven said, you can sum over spin structures if you want. That's one way you can do. Mod out the parity group. So mod out. What do you mean by it? Sure, you can. Yeah, this is a subgroup, so you can always gauge. This is what Juven was saying. You can always kind of gauge this part, which is summing over the spin structure, right? This is a subgroup, so you can. Mm-hmm. Well, I mean, bosonized is a more particular type thing, right? It's a special thing that if you really mean that type of bosonization, it's a more special thing of the theory itself. But this is a manipulation you could do with the symmetry structure. So to bosonize is a property of a theory, but this is a property of a symmetry. So I'm telling you a property of the symmetry, or Juven was telling you a property of the symmetry you can do. To bosonize a theory is something that you have to study a bit harder. Okay, so a relation between this and spin structures. So you can think of this categorical symmetry as kind of saying, well, I have some twisted spin structure in particular. So imagine so as I was saying, imagine you just started with a theory with like no symmetries, but you had fermions. Then that says that the tangential structure has to be a spin structure. So if you just have, so if you have T with no global symmetries, no global symmetries, i.e. like GB is trivial, then the fact that it's fermionic means that you need to make sure that pi2 of whatever tangent space that you define your theory on is trivial, equals 0, and of course pi1, or sorry, W1 of Tm equals 0. So these two together enforce the fact that your manifold is spin, so imply that M is a spin. But now, if T also has T, now you give it some symmetry. So now you have T kind of with GB symmetry. then what I can have is I can have a twisted spin structure. Which is to say that, which is to say you should think about T as having two types of bundles. It has the tangent bundle, and then it also has something about like a G bundle. And what you want is you want to say that, well, you want to have some kind of trivialization of, you don't necessarily need to have W2 being equal to 0, but in particular you can say W2 is equal to, let's say, kappa, and let's say W1 of Tm let's just say equal to 0. So this is going to be the important type of spin structure I'll consider today. So kappa was the same kappa from the other board, which is just to say that there's a way of twisting this condition by a condition on something about the GB bundle. So these two kind of together can cancel out. The precise way of saying is that you have a spin structure on the sum of the tangent bundle with a vector bundle over here. So, sorry, yeah, so if you have no symmetry at all, then exactly you would have something like this. And if you have some symmetry, then you can say that, well, to say something has a G symmetry means that it has a G bundle, and to say that it has this thing means that it can have a twisted spin structure. So I can trade this action for a structure on the underlying manifold, right? And to say that you have an action by -1 to the f is somehow saying is sort of this type of condition. So this will be important later on for the story. So if you have something like this, then I'll call this rather than a spin structure, the spin manifold, then I'll say M is a spin GF manifold, which is just to say that so the precise definition of this is you take the spin, and then you multiply it by GF, and then you mod out by the common Z2. So these two are identified. If you like, you can write this as a pullback of GF and then spin, and then they're identified with the common Z2. So this is a type of pullback. And the pullback identifies these two cohomology classes, which are maps into Z2. Okay. So, all right. So much for the symmetry. So one more thing I need. So here's one. If you want like a spin, so a type of twisted spin structure, for example, is like a spin C structure, which maybe is familiar. So you have things charged under U1. So you have a spin in a U1, and then you mod out by the common Z2. So the fact that your electron has some U1 charge, right? Like you might not have a spin structure, but the fact that your electron has some U1 charge, the failure to not be on a spin structure is canceled out by the fact that you pick up some polynomial under the U1. So that's an example. So I could, that would be basically spin dash U1 is spin C. Does that help?
Yeah, I mean, I guess so. T 2+1d. Q, just regular QED with some fermions and flavors.
Sure. Yeah. I mean.
You're assuming that there are just spec lines.
Yeah, exactly. So something like that could be an example. But pick an example so that I'm working completely general, but indeed you can pick an example as you said, but I just need those conditions on the symmetry. So it should have only surface operators as symmetries and no line operators as the symmetries. It's not super easy for me to give you an example of such a theory, but hopefully it's not the empty set. Okay, great. Then it is not then I'm not proving a property of the empty set. Cool. So that's sort of the important thing that I wanted you to take away about the structure of the symmetry. So in particular, fusion 2 categories have been classified. But this is a special type of fusion 2 category. It's a very simple type of fusion 2 category with no lines. So this also admits a classification. So there exists a classification classification of fermionic, I'll just say fermionic strongly fusion 2 categories. And the classification goes through, which goes through something called supercohomology. Which is to say that these types of categories emit a classification which is just group-like. I mean, that's maybe not so surprising. There's nothing about it that's one categorical that goes into this classification, even though the classification of general fusion 2 categories does have something that's one categorical, but since there's no lines, then that's good. And so it just goes through something that's group theory and then something that's like cohomology like. So I want to describe to you a little bit about supercohomology. So this is going to be an important kind of thing in our story, so I'll have to go through this. This is not just I want to advertise for you classification results, although maybe you care about that type of thing. So what is supercohomology? You can define supercohomology in, let's see, I probably have 3 ways of defining it now. I could define it in 2 ways, and then you can pick your favorite one. One way of defining it is as a truncation of KO. So you can consider the exact sequence. So you can take the homotopy groups greater than or equal to 4 of connective KO. You can map that into regular KO, and then the cofiber becomes tau less than or equal to 2 KO. The reason why I skipped 3 is because 3 is equal to 0 here. And then what I can do is I look at this thing, and this has homotopy groups. So pi 0, pi 1, pi 2 over here. This is Z2, Z2, Z. And what I want to do to define supercohomology, superco is I want to take the Pontryagin dual or the C star dual of tau less than or equal to KO. For shorthand, I will call this SH of a point, probably. So it is a spectrum with 3 homotopy groups, and instead of Z, it has C cross sitting at the bottom. So this is kind of an abstract way of defining things. You could say, like, why do I care about such an object? What did it have to do with fusion 2 categories? The answer is a priori not very much. Other than actually using this type of sequence actually gives you some pretty nice handles on how to compute supercohomology for certain groups. So you can kind of feed this into some nice atom spectral sequence stuff, which is things I'm currently working on, and it actually gives you a nice way of computing supercohomology via this hastened atom spectral sequence. Just like how the atom spectral sequence would help you compute like Bordism groups in general, there's a way of computing kind of truncated Bordism groups using other spectral sequence techniques, which I think is pretty fun. The second way of defining supercohomology is you can consider the following 2 groupoid, which looks like the invertible parts of 2s-vec. So this has 3 layers, and then if you look at them, so 2s-vec, you can also think, if you like, it's the same as the Morita category of superalgebras. And then this one has the same homotopy groups as this thing as well. And there's of course some K invariance in here. So this is also the same as SH, if you like. Now there are some K invariants that I should tell you about. So there's this kind of this pi 2, which is supposed to be Z2, and then there's this pi 1, which is C2, and then 0, which is C cross. And then if I want to tell you about the K invariance, then there's a map from K invariance would go this direction. And then this thing is the Stirner operator square 2. And then here you take the exponent of the Stirner operator square 2. So this eats in a thing. this eats in a thing in this type of cohomology. So then now these are the k invariants of this of this thing. These are also, of course, the k invariants of KO as well. So you can study them from there.
So you might just sort of
Yeah, sorry.
So I understood. Okay, so the first part, I understood that you have S vectors, your set of lines.
Yeah.
And then you have these surfaces that realize some group. And now here you've written a lot of abstract stuff, I guess, that lives on top of that group to really classify the fermionic, whatever, strong.
Yes.
Strong
Yes.
Can you relate any of this stuff? Like, I guess the additional data is probably related to like junctions of surfaces and stuff.
So the reason why this makes an appearance is because at the end of the day, the types of categories that you would want to get of this form are going to be some sort of, you can really do it from extension theory. So you take something like this with no symmetries and you just apply some extension theory there. And extension theory works by mapping into exactly the invertible things here, if you just by the ENO extension theory. And so mapping into something like this essentially gives you maps into SH. Maps from, let's say, a group BG into SH gives you some super cohomology of BG in degree 4 because it's a 2 category. And so
Is it possible, like maybe it's too much to draw diagrams and stuff, but is it possible to sort of draw diagrams and explain sort of this additional
yeah.
in terms of the surfaces, meeting points of surfaces?
Right. So the way you can think about this is, so what I would like to do is I would like to say these types of strongly fusion 2 categories are GB graded extensions of this thing, right? So you can think of this from the point of view of, let me give you an example that's maybe more complicated that you need, but take Chern-Simons theory. And Chern-Simons theory may have some symmetries, right? So now what you want to do is you want to say couple Chern-Simons theory onto the symmetry. The category you get is you get a G cross braided extension of Chern-Simons theory. Certain G cross braided extensions are classified by, in particular, cohomology. So I want to do the same thing here, right? Except I don't need to worry about line operators. I just need to worry about surface operators. So it really feels like a group-like, it feels like a higher group-like extension theory, basically. So, so exactly. So there's some obstructions that must vanish here. So here the obstruction theory is basically I need to map into this guy, which parameterizes for me all the extension theories. So this is essentially taking in some of the GB things as like surface operators and like inserting them inside your theory. The same way that you would do extension theory for like Chern-Simons theory is that you include these flux sectors basically that give you some G-graded extension.
So I mean, in the G-graded case, you have,
No worries.
In the G-graded case, you have some H4 extension, right? Some H4
Yeah, that's right.
And you have like some stack SPTs, and then you have some fractional relation.
Yeah.
Like, are there similar concepts in this case?
Yeah. The way you should think about it is somewhat similar. Yeah.
Is there some version of H4G?
Right. So the Tooft anomaly will be in degree 5. Yeah, and the classification, like the data itself, is in degree 4. This is the analog of an H3 class that you would do for like 1 categories, basically, right? The types of thing that you would classify with Tenbari Yamagami or something like that. The thing that's not the anomaly that actually gives you certain classifications is H3. So for example, the Fabrini-Schur indicator is an H3 class. And so the thing that classifies the right extensions you want here are H4 class or SH4 classes. The anomaly is 1 degree higher. Yeah, it's just but this is fermionic.
Yeah.
So that's your. So 2 things. So Chern-Simons is in 3D, but this is a 2 category, right? So I'm 1 category level higher, which shifts my classification degree up to 4, and the anomaly becomes a degree 5. The reason why Chern-Simons is the TQFT in 3 dimensions built on a 1 category. I'm talking about a quantum field theory, which is not topological, but the symmetry itself actually deserves to live in 1 dimension higher, and so that's why it's an H4 class. Yeah. Great. So actually, thank you for asking that question, because then it makes it clear why SH is defined as something like this, which may be helpful to people. But I kind of like this definition because it's actually very handy in terms of doing computations. So cool. So okay, after introducing all of that stuff, I can finally give you the construction. It's been 45 minutes. Dev, I'm doing worse than you. All right. So, oh, actually, there's one more thing. Sorry, there's one more thing I wanted to say about this that I forgot. Another helpful way of thinking about supercohomology is that if I take supercohomology of, let's say, a group BG in some degree, then you can realize this as some cocycle, right? There's some alpha, beta, gamma cocycle here that you would wanna say. Just because it's 3 layers, I have kind of 3 cocycles. So alpha is in C minus 2 BG with Z2 coefficients. So I'm going to run myself out of space, so maybe I should go a little bit higher. So you take supercohomology BGB, that you can get as an alpha, beta, gamma cocycle. So I'm just going to tell you some conditions that these cocycles satisfies. This is in degree star minus 2 BGB Z2 minus 1. This is C cross or U1 if you like. Now there's some conditions that there's some equations that you want to satisfy. Namely, the differential acting on this is trivial, so this one actually becomes a cochain. It becomes actually a cocycle. This one you want to have d beta is equal to square 2 plus, so you're going to want to plus kappa. So actually I want a twisted version of supercohomology for technical reasons. And then d gamma is some equation that looks like minus 1 to the power of all of this. Beta, and then there's another term that depends complicatedly on alpha and kappa, which is correcting the fact that this was not closed. Okay, so that's the data I needed. That's the data that I wanted to provide you about supercohomology. So now you have 3 ways of thinking about this type of object. This way is, so this way really, I mean, they're all related to each other. Having this cocycle description is quite nice because I'm going to be playing around with this a little bit. One thing I should say is that this supercohomology tells you something about the extension, right? And so fusion 2 categories are classified by these 3 types of data. And in particular, there's one important piece of the classification, which is really the group structure. And the group structure has something to do with alpha, right? Alpha here, if you look at it in degree 4, this is going to be an H2 cocycle. And so this is going to have something to do with the extension structure here of GB with Z2. So bearing that in mind, now I can give you the actual construction of what I'm going to do. And now this is where emergent fermions are going to come in. So here's the construction. I take my theory, and then to it I stack on a 2+1d TQFT, which takes the form of spin and level 1. So this is how I want to do things. Now, when you do this stacking, you realize that there's something that there's some algebra. So you would have naively said this is a weird thing that you're doing. You're taking a theory that was all well and good, and then you're stacking on it a TQFT, which seems like you're modifying the theory quite a bit. That's maybe not so good. But there is a thing that you can do inside here, which is that this thing has an emergent fermion. So inside the spectrum, there's a fermion called F. So this thing is some sort of kind of generalized Ising category. When n is 1 and 4, mod 16. So n is a mod 16 number. When it's 1 or 3 mod 4, it looks like Ising. It has 3 objects. When it's like 0 mod 4, it looks like the Torah code. And when it's 2 mod 4, it has an object in the dual object, but it still has 4 things. They're always invertible. Point is that this is the emergent fermion that's inside here. So it's a bosonic theory, but there's a spin 1/2 object, which is why it's emergent fermions. So it's a bosonic TQFT that I'm stacking onto a fermionic theory. What I'm going to do is I'm going to condense a boson. By condense a boson, I mean that there's an algebra inside here that's fully commutative. And this algebra is going to look like basically 1. It's going to kind of look like 1 plus 1 plus psi. Sorry, I should write tensor this f. So what I'm saying is that inside here there's an object which is like the invisible fermion that is this. And I can stack that with this guy. This creates a bosonic object here. This gives me a bosonic algebra which I can condense from here. And what I'm actually doing is, so here you had a copy of supervector spaces inside the lines. Here you have something like this. And if you study this following Morita equivalence, you can look at something like this. So you can take SOM level 1. So SOM level 1 is basically how you can represent supervector spaces. This is a monoidally equivalent. The only difference is that there's a central charge here, which is actually going to be important for the story. So this has the same object as supervector spaces. So this is a thing which this theory contains. And then now you stack on with it. Oh, maybe, yeah, the notation here means D loop plus or connotation complete, if you like, idempotent complete. So what it means is that these were line objects, but then now I kind of fill them up and I make them invisible surface objects. And then you can look at this spin n level 1 by condensing this algebra. So when you condense A, you get something that looks like SON minus SON plus m level 1. And this kind of makes sense from the point of view that this has some central charge, which is m over 2, m over 2. This has some central charge, which is n over 2. And so, what I've done is I've done some manipulation where I've taken a TQFT, stacked it on. I've condensed this thing out. So basically, in condensing this out, I've killed all the interesting topological operators that I've introduced. And then now, at the end of the day, it's basically equivalent to, well, it's equivalent to the theory again. But then now I added some n over 2, maybe a gravitational term. The symmetry is still the same. For sure, for sure. That's right. So that's right. So this doesn't work. The only theory in which this procedure will work is this one. And the reason why this works is because there's a theorem in Fusion 2 category literature. So if you take 2S-vec and you tensor on with the Cherebian completion of C, where C is one of these spin n level 1s, there's a Morita equivalence back. There's a Morita equivalence back to 2S-vec. This is actually a really subtle point. In the fusion category literature, this C is something called a minimal non-degenerate extension of 2S-vec. There's 16 of those, which is why this is a label in mod 16. And this is quite a headache, actually. The reason, because you have this Morita equivalence, it makes the fermionic classification of fusion 2 categories very subtle. But secretly, this is actually using this Morita equivalence fact, and this is the only category that works. It has to be a minimal non-degenerate extension of supervector spaces. That's right. And indeed, if I did something else, then you'd be like, now you're actually cheating because you didn't just stack by an invertible thing at the end. But here, I just changed the central charge, which means that the theory is the same up to the central charge. So we'll get back to that. But I want to say that C is not the same. C has actually changed a little bit. Or maybe I'll call it C tilde. So what I want to convince you is that this procedure leaves this theory invariant up to a central charge, but it modifies the symmetries of C. So here's one of the theorems in the paper.
16. If I don't even know category theory, I know the fact is, this maybe like detecting full manifold with spin or non-spin structure. That can come as some manifold generator. The bosonic one is the what's that? The CP2, right?
Yeah. Yeah.
And then the fermionic one is K3. And the relation between the signatures a factor of 16. And this is maybe more on the mathematical like index theory side. And in physics side, say the H modes of the corresponding 4D invertible TQFT term. TFT term is the P1 over P1 from the first polynomial class of P1 over 16.
Mm-hmm.
So then the corresponding H theory from the gravitational transaminant point of view by reduction from P1 written as on D gravitational transaminant, then H mode has this chiral central charge, either the EA CFT as EA central charge 8 and the Marana biofermion central charge 1/2. So this is more like intuitive to me. So how about from this point of view, do you offer something different perspective? Just give me some sense, because you say out of the 16 out of this coming from something seems like a Bible or something. Is there some statement like make it obvious?
Well, I think what you said might be related to the central charges of these spin-in level 1 theories, because these are also the central charges of each one of these guys is n/2, and this is and is mod 16. No, it's not quite easy for me to recover what you just said about the invertible things in 4 dimensions using this. I mean, they're probably related, but they're not. It's not quite obvious. Yeah, because here's another thing, right? What you're looking at is the oriented and spin bordisms of a point, right? And right, which is just the invertible TQFTs with no symmetries, just with the right structures. Here, I mean, yeah, this is a good question. I wouldn't know how to relate this modular tensor category to some invertible thing like that very easily.
But you just use some factor, bosonization, 16. You just said that, so that's fine.
Yeah, you can study. Well, actually, right. You can study these types of things, and then you can study what classifies these types of things. So there's a paper by Barkashli et al. that kind of classifies these types of things, and by bosonization, they also classify these types of things. Yeah, it's interesting comments, but I wouldn't necessarily use that intuition in 2+1 dimensions. Okay. So right, so that's the construction that I want to do, and I want to say that the symmetry actually changes. So right, so the theorem is under the stacking algorithm, under the stacking plus condense row this procedure. C changes as follows. So C itself was supposed to be classified. So C is itself classified by some class, let's say omega, inside SH4, some twisted SH4 class GB, which is just to say that C itself was some extension of GB by Z2. And then a cohomology class basically classifies all types of extensions. So if GB, as follows. So right. So if kappa equals 0, then omega experiences no shift. And what I mean by experiences a shift is this thing was itself a cocycle that looks like this. But if kappa is actually trivial, then if you do the stacking and condensing procedure, experiencing no shift just means that these cocycles never got modified. And I'll explain to you how the modification actually works. Let me just say the result quickly. If kappa is non-trivial and square one of kappa equals 0, then this thing is 2-periodic. Meaning that if I stack on some Sn, then that'll change it. But I stack on it again, and then it comes back to itself. If kappa is not equal to 0, and square one of kappa doesn't equal to 0, then this thing is 4-periodic. So I do it 4 times, and I come back to itself. And under so a single iteration in one of these cases where it's actually non-trivial, what does it do? It takes alpha, beta, gamma into alpha plus kappa. This actually makes sense because alpha is the same type of kind of cohomological object as kappa. A single iteration of one of these procedures. A single iteration of that takes this thing to this. It takes beta to beta plus kappa cup 1 alpha, and it takes gamma to some complicated mess that depends on this. So that part is not so important. And indeed, this is actually, so if you believe me that this is true, I'll explain to you why this is true in a second. Then the symmetry no doubt changes because this extension class this extension class actually changes. So kappa itself was something about the extension. Alpha is also an extension. And so in particular, if I take alpha to be equal to kappa, then I could start off with something where alpha is non-trivial. So I have a non-trivially extended group. But then I could trivialize the extension by here. So I can go from a Z4 type thing to like a Z2 times Z2 type thing by this. And this is a very, very different type of symmetry. So indeed, the symmetry structure changes. And now let me try to convince you really quick why this happens. The reason why this happens is kind of sneaky. So there's right. The reason why this happened is because if you consider kappa, if you consider GF is equal to Z2 kappa GB, and you consider the fact that what did I do? Well, I stacked on some other theory with an emergent fermion here. And so what that does is basically you can think of this kappa as some sort of GB fractionalization data. So you can think of kappa as kind of a GB on like the Z2 symmetry. And well, first I need to actually show for you that this changes by sorry. So you start off with kappa being some GB fractionalization data, and then you realize the fact that upon condensing the algebra, the algebra A over here, alpha was initially some extension data. Now, when you stack these two together and then you condense the algebra A, it is just a fact that the fractionalization data becomes extension data. This is actually, I mean, it seems like I'm citing this fact, but this is actually quite a well-known fact that when you gauge essentially by the Z2, right? Because you're kind of stacking on it and you're condensing this pair of the Z2, then this thing which was fractionalization data becomes extension data afterwards. And there's multiple ways of seeing this. The paper by Yuji Tachikawa on gauging finite subgroups explains this. You could also see this from the point of view of the spectral sequence. And so essentially, this is the first step that you want to run to convince yourself that the fractionalization data becomes extension data, and therefore feeds into this. Exactly. So cool. So that's the first thing you see. And then you want to kind of trace this argument down, and you want to say assume that beta changes by some delta beta, where this is what happens after you stack. And then you realize that, well, there's some equation I need to satisfy, right? I need to make sure that this thing is equal to this, but then this, of course, has some property based off of the thing that I erased. But essentially, d beta prime has to be square 2 plus kappa of alpha prime. But alpha prime now is alpha plus kappa, and so you work it out, right? You work out this computation, and then you plug in what d beta was before in terms of just alpha. And then what you see is that delta beta becomes kappa cup 1 alpha. If you like, you can also say it's something like this. So this is an equivalent way of writing things. So this is just some algebra. And then you just you keep on doing this procedure, and then you discover that something like this is true, and you see essentially the right conditions by noting the fact that kappa cup 1 kappa is equal to square 1 kappa. So in doing these manipulations, something like square 1 naturally shows up, and if it equals to 0, then you get some cancellations, and it ends up being 2 periodic or 4 periodic. So that's the last part of the computation. Okay. Right. But also just because like this whole like sneaky little thing doesn't even quite work, and the classification isn't even given by supercohomology. So like this whole thing like doesn't even work. It's much more complicated because then the classification of fusion 2 categories really needs a part which is something about modular tensor categories. So you really need some action on a modular tensor category which describes the lines of a general fusion 2 category. So this trick doesn't work there. But the reason why this trick is useful is because there really is, now that you've told me, like there could be some quantum field theories which experiences this type of change in the symmetry. Because, well, this is sort of the most telling thing. And I just want to say that in this story, right? What did I do? I went from T with a C action to it's the same T but plus some, let's say, gravitational counterterm, and then now I have some C tilde action. So this is I'll call this as the stack plus condense route. But you could have also done something like, instead of stacking plus condensing, well, here's something that you could have done, is you could have just said, take T, you stack on to it just an invertible thing. So you just stack on the spin m level 1 that does the correct change. And now the symmetry doesn't change. So this is the interesting thing. I've taken two paths in terms of what I can do. And here the theory is the same, but the symmetry's changed. Because, so this is the thing, right? Like, I've made the theory equivalent at the end of the day, but depending on how this equivalence went through, I've changed the structure of the symmetry. Now, there's of course a very important caveat, which is in what sense. So now this is a very important caveat, which is in what sense are these two the same? So in what sense is T and T shifted by a gravitational countercharge the same? So let me just write this down in words. Oh, sorry. So if you believe, I mean, this is not really a belief, but you can detect this, of course. But let's just say you believe that T and T plus m over 2 are the same, are the same Q of T. Then then this is maybe kind of surprising, right? Well, usually when people talk about quantum field theory, you'd say that they're the same because the central charges thing is either a thing that you would detect by maybe coupling on to some background, like coupling onto some like gravity, or of course you can take this theory and put it on some manifold with a boundary, and you could detect this gravitational thing. But if you didn't do something like that, you just thought about quantum field theory, most people would be pretty happy with saying that these two things are the same. So then, of course, yeah, this is to say that this is a little bit weird. So how do we resolve this issue? I would like to say something like we would like to be able to distinguish these two types of things and these two types of equivalences. So the cop-out that you could, so one solution to this is you can say, well, actually, QFTs should be a valent object, where I really say something like, or sorry, you could really say something like, suppose I don't want to say that I have to make a detection of a QFT by putting it on some manifold boundary or something like this, and you really say that these two things are the same. Then you'd have to kind of upgrade your symmetry condition, right? You have to allow yourself a little bit more about what you mean for a theory to be the same. So you have to allow something like this into your list of conditions. If instead you wanted maybe a more valent thing, and you really wanted these two things to be the same, then I would say that somehow, like the right way to make the category of quantum field theory as a valent object is you somehow say that not only do you just study quantum field theories, but you also have to say something about being able to detect the central charge as part of the conditions as well. And then in that sense, you could tell, and then if you put that into your definitions, then you would be able to actually distinguish these two types of things. And then it's not so surprising that they have different symmetries. Okay. So that was the discussion that I think is maybe the physically more interesting part. And then since I have 15 more minutes, I just want to finish the rest. I'll finish the rest of my talk quickly by saying that the numbers that you get are not actually random. So I want to put this in sort of a larger context. And right.
Example, you're saying that if it's univalent, then you can change the central charge and you can change the symmetry, and that would still be the same. Or you can only change the central charge, and that would still be the same.
So, right. You can either say that you'd want to say, right, yeah, right. You'd want to say something like, this theory is really somehow the same. Sorry. To say that this theory and this theory are the same means that you ignore the fact that you could detect central charge in any single way, right? You just say that I take a point of view of quantum field theory where I can never tell this apart, right? And then what you'd have to say is that, well, I have to allow some way of saying there needs to be a different equivalence condition rather than just, sorry, I need a different equivalence condition rather than just stacking itself. I need to allow myself the stacking and condensing procedure. So I need to allow myself to be able to stack by kind of non-invertible things. And this is what I would say is more of like a valent notion. I don't just want this level of equivalence. I want to say that this is also a reasonable thing of equivalence. If I'm working in a setting where I can never ever distinguish between central charges. If you want to say that you can have a way of distinguishing central charges, right? Then you don't actually need this other notion of equivalence, because you could just say, suppose I work in a setting where quantum field theories should be able to, you should be able to couple onto gravity or manifolds with backgrounds, and then these two things are different, right? And then it's not so surprising that I have two different types of symmetries. So I'm just saying, if you adopt the first point of view, where I can't tell the difference, then you need a different equivalence condition. If you want to be able to tell the difference, then it's not so surprising. And I'm saying maybe in the right definition of quantum field theory, we want to put in being able to detect the central charge into the space of quantum field theories. So that we should be able to know when two things are actually different by central charge. And the only way to do that is to say probe with gravity, or probe with like some manifold with boundary, this type of thing. So as a mathematically interesting, as another maybe mathematically interesting part of this talk, which I don't think I'll have too much time to get into, the numbers that I gave over here are not completely random. You can actually prove some interesting relationships between these numbers and some other things. And so the theorem is the following are equivalent. So on the one hand, we have the spin and level 1 such that stack plus condense on T leaves the same invariant. Number 2 is you can look at the image of the following map. F that goes from the group of minimal non-degenerate extensions. Okay, I'll explain what this means in a sec. But let me just write this down. So there's a group called the group of minimal non-degenerate extensions of braided fusion 1 categories B with the Z2 center of B given by this. So those minimal non-degenerate extensions form a group which is called this thing. And then this guy is the Z16, right? So this is all such minimal theories. I didn't even define for you what a minimal non-degenerate extension is. But yeah, so what this is basically you have a thing where you have a Muger center, so there's some invisible objects inside here. You want to take B and you want to extend it to some bigger category C, such that this thing is actually non-degenerate, but then the only objects, and then such that this thing actually does become non-degenerate, and the only things that were kind of invisible were already these guys. So you didn't add an extra thing. So for example, the center is not a good thing because the center has like way too many other objects, and so you really want like the smallest thing that you can extend this by is the minimum thing, which is why spin n level 1 happens to be an example. And good. So you want so what does this map do? This map takes a category that's inside here. So oh, by the way, so E here is some super Tanakian. So it looks like rep GF. Now, given a super Tanakian thing, you can of course de-equivariantized by the maximum Tanakian part inside here. And the maximum Tanakian part I'll call C0, which is C you de-equivariantize by F. That's the maximum Tanakian part with Vec. And so what this map does is it takes C, it squeezes out the maximum Tanakian part, and it just leaves you with C0 over here. So that's what this map does. So you can study the image of this map. Yeah, yeah, exactly. So you're just left with a super vector space part. And then 3, you can also study those spin and level 1 that can be compatibly coupled the background spin GF structure set by the initial symmetry C. So the fact that these two are related are maybe not so surprising, and then you need to do a little bit of work that can also involve the center of this category to show that these two are equivalent. But this kind of sort of tells a nice story and ties in this whole thing between kind of Brady fusion 1 category stuff and interesting things you could do with symmetries in higher dimensions. Okay, so in the interest of time, I'm not going to prove this because it's probably going to take a little bit too long, but I'm happy to take questions if people are curious. And yeah, thank you for your attention. Yeah, so it depends. It depends on the structure. It depends on the structure of the symmetry. And depending on the structure of whatever category you turn in, then those ends will leave it actually invariant. So it depends on the only conditions I'm thinking about are these types of conditions. So given this, what are the ends that leave it invariant? And you'll always be able to find some that leave it invariant.
Does it mean that the absent gravity that two theories have the same correlation functions? Or are we working with a more abstract notion of equivalence?
Yeah, so I would say that the more abstract notion of equivalence you're working with is you want to say that this is a type of equivalence condition you put on your thing. Though the correlation functions I don't think would be interrupted. I mean, there may be some more kind of subtle things going on in the middle, that there's some kind of fractionalization that actually happened when you stuck things in and then you kind of condensed it all out. There may have been some fractionalization that happened to these correlation functions, so you have a different symmetry. Like maybe that's the way you want to interpret this type of equivalence condition, as doing something like that. But I'm not quite sure. I haven't actually explored like what it actually does on the microscopic level. All I know, I haven't explored on the level of like correlation function. All I know is that the local observables have not been changed at all. But it could be that somehow when you look at correlation functions, something weird happens when you actually allow for this thing to come in here. But I would just stick it all into this type of equivalence condition. That's the new equivalence condition you allow for quantum field theories.
Change the symmetry without changing the correlation function. Usually the correlation functions like depend on the symmetry. And there's some correlation functions that vanish one symmetry, and it's weird. You change the symmetry, but they still vanish for no reason.
Yeah, so it could, yeah, right. That's why I'm saying that, you know, if you did a detailed study, you'd probably find something like this. That's what I believe.
I mean, this is naive because I think maybe I shouldn't press you to say that this is not your talk, but I guess you mentioned this Z2 extension fermionic things people discussing earlier, but I mean, we know the DM case and terrafermion I just want to come back to ask, is there some additional thing special for the Z2, but not happen when we go to Zn? From the perspective, you can say, oh, is there some difficulty when we do the story for Zn?
What do you mean by like difficulty, or like what's the thing you're?
All the property might be different. Let's say.
Right. So the thing that you would want that So one thing, for example, is that this thing is really a double cover. So if you did an n, you have to do an n-fold you have to do an n-fold cover, for example, right? So something like you have to spin around n times or something like that, to come back to yourself. But I'm not sure if that's the type of answer you asked for, because that was too obvious of a thing that I said. So maybe you wanted something more sophisticated. A more sophisticated thing I could say is that this algebra, or this algebra that I'm supposed to condense, which was just a fermion and something else, it's hard to like pair up something like that if it's not 1/2 to get like a boson at the end of the day, right? The fact that I take two fermions, I pair them together, I get a boson, but otherwise, like, it would be more complicated to find the right type of algebra if I want to condense like a boson made out of like spin 1/n things. That's quite hard to find. So if you just condense that rather than making a boson, then you'll get some spin. Then you'll get some like kind of n-fold spin theory, which people, I think Niels Karkeville have discussed before in certain papers. So if you just condense like a fermion, what you'll get is you'll get a spin thing at the end of the day, right? I condense the boson, so I get an oriented thing. If you condense this 1/n thing, you have some interesting other structure, which is some local like parafermion or whatever, or something like that, maybe.
An example of that might be like a string structure, right? If you lift even higher and use the spin.
So string structure is not quite the same, because a string structure is a trivialization of an integral class inside the Posnikov tower.
Right, but isn't there something you could, instead of taking Z2, maybe you could put in another factor?
But so all of these things are going to happen in degree 2 cohomology, though. But the string structure is not. So I actually don't know how to realize a low-dimensional topological phase with a string structure, because they all have string structures, right? It's always trivial in like low dimensions because it's the H4 class.
Here you explain this alpha, I guess, being related to an extension. So I kind of understand that as a group extension. Can you explain just a little more about this beta and gamma? What's sort of the physical interpretation of this beta and these shifts of gamma?
So this thing here, this thing here you should really think of as some sort of like, because it lives in the lowest layer, right? This would live in degree 4 if you're looking at a degree 4 supercohomology class with just U1 coefficients. So this behaves like a Digraph-Witten type layer. And then this is genuinely a little bit more complicated. It's the first step. It's the first fermionic layer that goes above cohomology. That goes above.
Would you say this gamma sort of relates to an SPT or something?
Yeah, this gamma is really like a bosonic part of the anomaly, if you want to think of these things as related to anomalies. They are, right? Because if you didn't think of it in terms of symmetries and you wanted to construct actual TQFTs, which is a totally different talk I could give, and you could actually construct a gauge theory out of something like this, right? Because you make an invertible phase defined by something like this, and then you gauge that symmetry, and then you get a gauge theory. And in this gauge theory, what you want to do is you want to write down some sort of state sum or something like this. And the state sum you want to build is some generalized version of using this Digraph-Witten layer with this extra layer called the GU1 layer with this Majorana layer. So it turns out that people have actually tried to write state sums using these two types of things. So there's a paper by Kobayashi, Omori, and Tachikawa that try to do this. But in order to do this, you need to introduce some fermionic variables. So you need to use this Gaiota-Kapustin path integral, where now you have some barycentric division of your manifold, but then you have to put on some Majorana fermions around some loops and things like this. But this is an extra degree of complication, and I don't think anybody knows how to write down like a state sum for a TQFT using all three pieces of data. It's not super easy to interpret this, because this is exactly, I mean, the reason for this is exactly because you have the groupoid for 2S vec is just bigger, right? The groupoid for 2S vec just includes 3 layers, so you have to have something like this. I'm not sure to what degree I will be able to unpack this, but that's the intuition you should have if you like TQFTs, things like that. this image of this map.
Basically corresponding to moving inside the orbit by the subgroup reflected by the image.
So the image of this thing, yeah, exactly. And the those subgroups are generated by those like spin end theories basically.